Hi, we're Tardigrade from the University of Texas at Austin, and we're excited to showcase and explain our solution for the Mars Autonomous Rover Rally Challenge. I'm Simon Chen, and we're a group of 6. The others are Mohammed Dawood, Trent Mosier, Jervis Benjamin, Sneh Memtora, and Ronil Shah. We also have our faculty, Dr. Maruthi Akella. Our solution focused on stability. Instead of complex perception or learning-based methods, we designed our control structure to be focused on simplicity and time efficiency, operating close to the rover's stability limit in order to achieve the fastest traversal while maintaining reliable autonomous behavior. So our solution begins by solving the navigation problem. So what is the most efficient way for the rover to navigate to all 20 waypoints by only going there once? And we solve this by using the held carb algorithm, which finds the minimum distance for the rover to travel to get to all 20 waypoints. Then, for how to get there, we use a set of conditions based on the rover state. This will determine how the rover behaves when encountering conditions like running into a rock. In parallel, we're also trying out different techniques such as convolutional neural network to detect rocks and a guidance algorithm to move around those rocks. We're also tried pitch-dependent acceleration, which will keep the rover stuck to the ground, and that will ensure stability and maximum speed. So while these techniques are promising, we did not implement them due to time constraint. They were inconsistent, and we didn't have enough time to fully integrate and solve the issues that we were having.
The CNN that we did develop used contouring on the raw depth images, which after some testing we found to be much more accurate. In order to avoid overfitting to these few hundred images that we had, though, we used heavy augmentation of our dataset, as well as shuffling and batching. And to handle the sparse population and large size variation in the rocks, we used a weighted BCE and dice loss function. In the end, we estimate that the error on our CNN was on the order of around 1 in 100.
To make sure the rover can avoid obstacles, we developed a object avoidance algorithm which combined the CNN model results in addition to the depth camera to determine if a rock collision was imminent, in addition to tracking the rocks we ran across. When we integrated and tested our algorithm with the sim, we found that there was a level of balance required between the sensitivity of the CNN model as well as how we would choose to renavigate. When we tested this guidance algorithm with the CNN model against our old methods, we determined that the previous version produced higher waypoints at a shorter time. As a result, we chose to use our previous model for this mission.
We now consider the case in which a rover is stuck on a rock. From our sensors, we gather information on our position and velocity. If a rover does not change its position and its velocity remains below a certain threshold, we start a simple reverse sequence that depends on our pitch angle, which is calculated through conversion between quaternions to Euler angles. This helps us reverse slowly when we're stuck on a rock uphill, so that we do not accelerate quickly down a hill and flip over or cause other instabilities. After reversing, the rover starts steering away from the obstacle, then returns back to navigating to its waypoints. We noticed that sometimes this sequence was not enough to help us escape from certain positions, so we implemented a feature called impulse mode. In impulse mode, a rover is commanded to full acceleration backwards while receiving random steer angle impulses that make it harder for the rover to remain wedged in the same configuration and increases the chance of breaking free from the obstacle. If the rover cannot reverse at full speed, it automatically switches to full forward acceleration instead. Finally, the rover detects if it has escaped or not depending on the distance it had moved away from its stuck position, then it returns back to navigating to its waypoints. Finally, I would like to talk about our dynamic speed limit. The main challenge in increasing the speed limit was that the rover loses stability over small hills in the Martian crater, which can lead to it flipping over. So, we knew that we should increase our speed limit when we move on a flat terrain and decrease it when we're on a hilly terrain to balance both traction and speed. To do that, we utilize the time rate of change of the pitch angle. To calculate that value, we use a simple definition of the derivative, taking our pitch angles at two different measurements at two different times and dividing that by the time it took for the sensor to send both readings. We then used a remapping clamper that clamps our velocity to a high speed limit when the change of pitch angle is close to 0, and to a lower speed limit when the change of pitch angle is high.
Finally, we want to say a big thank you to the organizers and anybody who helped make this competition possible. Thank you for your time, resource, and support throughout this competition. This competition has been a fun and really meaningful learning experience for us. We appreciate the opportunity to be a part of it.